Welcome to Sleepy Science Stories. Tonight we drift down smaller and smaller until we reach the Planck length, the mysterious scale where physicists wonder what actually happens when space, time and gravity break their usual rules. Imagine standing at the very edge of reality itself, where the universe draws a line in the fabric of existence. Here, at approximately 1.61 times 10 to the negative 35 meters, we encounter something remarkable. This is the Planck length, a boundary so profound that our most trusted laws of physics begin to waver and fade. It is the place where quantum uncertainty meets the immense pull of gravity, where they collide in ways we are only beginning to understand. Move any closer, peer any deeper, and space-time itself starts to behave strangely. It flickers and trembles like interference on an old television screen, like cosmic static filling the void. Tonight, we will explore this mysterious frontier together. We will do so with calm precision and gentle curiosity. We will examine what distance truly means when our measuring tools lose their power. We will discover why concentrating energy into impossibly tiny regions causes those regions to collapse inward upon themselves. We will uncover how atoms, light, and the entire universe seem to whisper the same fundamental rule over and over in different languages. So settle in now, find a comfortable place to rest, breathe slowly and deeply. Let your curiosity remain awake while your body begins to drift toward rest. Before we begin this quiet exploration into the heart of cosmic mysteries, I want to share something with you. If you feel at peace here in this space, if these gentle journeys through science bring you comfort, a soft tap on the like button or a quiet click on subscribe would mean more to me than you might imagine. It is such a simple motion, barely a movement of your finger, and yet it carries genuine warmth across the darkness of space and time. It is a reminder that somewhere out there, beyond my view, minds like yours still pause to listen, still take time to wonder about the nature of reality. Every small gesture you make helps keep this calm corner of the universe glowing softly in the vast digital cosmos. I am deeply, deeply grateful that you are part of this journey. Your presence here matters. Now, with gratitude in our hearts, we drift gently into part 1. Part 1. What truly breaks when we try to see smaller? What happens when we attempt to look deeper and deeper into the structure of reality? If we could somehow keep magnifying our view forever, moving past the realm of atoms, past the inner world of protons and neutrons, past even the tiniest building blocks called quarks, would the universe continue to reveal new layers of intricate detail stretching onward without end? Or would everything simply fade away into absolute blackness, into nothingness? This is not merely an exercise in imagination or philosophical speculation. This is a genuine, pressing question that the field of physics has been wrestling with for more than 100 years now. Every single time, humanity has constructed a better way to observe the microscopic world, from the earliest glass lenses ground by hand centuries ago to the colossal particle colliders we operate today that stretch for miles beneath the surface of the Earth, we have been following the same fundamental rule. It is a rule carved into the very nature of observation itself. To see smaller structures, you absolutely must use higher energy. That is simply how the universe works, how observation functions at its core. Light, like all waves moving through space, can only reveal the presence of objects that are larger than the wave's own wavelength. The light that reaches our human eyes, that beautiful rainbow spectrum stretching from deep red to soft violet, has wavelengths measuring hundreds of nanometers in length. That means each wave is roughly 1,000 times wider than a single atom. So even if you constructed the most powerful optical microscope imaginable, even if every lens were ground to absolute perfection, you still could not reveal the structure of atoms using visible light. The wavelength is simply too large, the waves too broad to detect such fine detail. To break through that fundamental limit, scientists began to use something else entirely. They turned to electrons instead of light particles. An electron, remarkably, also has a wave associated with it. This wave nature of matter was one of the most startling discoveries of early quantum mechanics. But the electron's wave can be made much, much shorter than visible light by accelerating the electron to tremendously high speeds. The faster it moves, the shorter its effective wavelength becomes. In the year 1931, a German physicist named Ernst Ruska built the very first electron microscope, proving beyond doubt that humanity could look far, far beyond the reach of visible light. By carefully adjusting and controlling the energy of the electrons, by making them move faster or slower, he could make their associated waves small enough to reveal the hidden structure of living cells, the geometric patterns of crystals, and even the shapes of individual molecules. It was a revolution in human vision, a new way of seeing the invisible. 3 decades later, at the Stanford Linear Accelerator Center in California, a place where physics pushed the boundaries of human knowledge, scientists took this same basic idea and pushed it to what seemed like its ultimate limit. They fired beams of electrons at protons with truly tremendous energy, with tens of billions of electron volts coursing through each particle. When those high-energy electrons struck the protons, something remarkable happened. The way those electrons scattered, the angles they bounced off in, the patterns they created, revealed something absolutely stunning. The proton was not solid at all. It was not a simple, indivisible ball of matter. Hidden inside each proton were smaller components, tinier building blocks that we now call quarks. That groundbreaking experiment, known to physicists as deep inelastic scattering, became one of the most important and celebrated discoveries in all of modern physics. It demonstrated beyond any doubt that matter itself possessed yet another hidden layer, another level of structure concealed beneath what we thought was fundamental. From that pivotal moment onward, we understood a simple but profound rule woven into the fabric of nature. To explore smaller and smaller distances, to peer deeper into the structure of reality, you must use higher and higher energies. There is no way around it. This rule has been tested and confirmed countless times across different scales of nature. Want to see inside an atom, to glimpse the electrons orbiting the nucleus in their probability clouds? You need energy in the range of hundreds of electron volts. This is the scale where chemistry happens, where bonds between atoms form and break, where the familiar world of molecules takes shape. Want to see inside the atomic nucleus itself, into the realm of protons and neutrons bound together by the strong nuclear force? You need billions of electron volts, thousands of times more energy than what is required to probe atoms. This is the scale where nuclear physics operates, where the sun generates its energy through fusion, where radioactive decay transforms one element into another. Want to see what might be smaller than a quark, if anything exists at that level beyond our current understanding? The energy you would need becomes truly unimaginable beyond anything we can currently produce, beyond perhaps anything that can be produced anywhere in the observable universe. This progression is not arbitrary. Each jump in energy takes us to a realm where new forces become important, where new phenomena emerge, where the rules change in subtle but fundamental ways. At atomic scales, electromagnetism dominates. At nuclear scales, the strong and weak nuclear forces take over. And at the Planck scale, gravity itself becomes a quantum force, no longer the gentle curvature of spacetime we experience in our everyday lives, but a violent, fluctuating field that tears and repairs the fabric of space itself billions of times per second. But here is where we encounter the trap, the cosmic catch. When we pour more and more energy into a smaller and smaller region of space, when we concentrate that power into a tinier and tinier volume, we begin to fundamentally bend and distort the very stage upon which we are conducting our observations. We start to warp space-time itself. Einstein taught us, in his theory of general relativity, that energy and mass are not separate things, but rather two sides of the same cosmic coin. They are interchangeable, equivalent, unified. Concentrating too much energy, too much mass energy, into a tiny region of space creates a gravitational field so powerful, so intense, that space-time begins to curve dramatically around it. At first, when the energy is still relatively modest, the curvature is gentle and barely noticeable. Space-time bends just a little, like a slight depression in a stretched rubber sheet. But keep increasing the energy. Keep trying to zoom in closer. Keep attempting to see smaller, and something truly extraordinary begins to happen. The energy you have packed into that microscopic region becomes so incredibly dense, so concentrated, that it begins to collapse under the weight of its own gravity. It is a strange and almost paradoxical situation. You are trying to use energy to see smaller, to probe deeper, to measure more precisely. But the very energy you are using becomes your enemy. It creates a gravitational field so intense that space-time itself cannot support it. The fabric of reality begins to fold in on itself, creating a pit so deep that nothing can climb back out. The tiny region you are desperately trying to observe, the infinitesimal point in space you are attempting to measure and understand, simply disappears from view. It vanishes behind an invisible boundary that physicists call an event horizon, a point of no return beyond which no information of any kind can ever reach you. At that critical moment, your microscope, your measuring device, your carefully designed experiment has just inadvertently created a miniature black hole, a tiny region of space-time so warped that it has effectively cut itself off from the rest of the universe. That is the precise point where the universe, in a very real and dramatic sense, turns off the light. It draws a curtain. It refuses to let you see any further into its innermost workings. Beyond this threshold, beyond this fundamental boundary of energy density, no instrument conceivable can see any deeper into the structure of reality. This is not a temporary limitation that better technology might overcome someday. This is permanent and absolute. Nothing at all, not even light itself travelling at maximum speed through the vacuum, not even gravity waves rippling through space-time, not even information encoded in quantum states, can escape from the immense gravitational pull you have created through your attempt to observe. The black hole you have made swallows everything, including the very answer you were seeking. Physicists have worked hard to estimate this critical scale, this ultimate boundary. It is called the Planck length, named after Max Planck, one of the founders of quantum theory. The Planck length is approximately 1.6 times 10 to the negative 35 meters. That is a number so extraordinarily small that it utterly defies human imagination. Our brains did not evolve to grasp scales this extreme. To give you some perspective, to help you feel the scale even slightly, imagine if you could somehow enlarge a single proton, one of those tiny particles in the nucleus of every atom, until it grew to be the size of planet Earth. Even then, even at that enormous magnification, the Planck length would still be smaller than a single atom sitting on the surface of that Earth-sized proton. That is how incomprehensibly tiny the Planck scale truly is. At this scale, at distances measured in Planck lengths, space and time are no longer smooth and continuous, as they appear to us in our everyday world, as they appear when we walk through a room or watch clouds drift across the sky. They no longer behave like the calm, flat, predictable stage upon which events unfold in an orderly manner. Instead, they ripple and fluctuate wildly, chaotically, boiling and churning like the surface of a pot of water at full heat, like the ocean during a violent storm. Imagine standing on the shore and watching waves crash against rocks, foam flying in every direction, water molecules leaping and spinning in complete disorder. That is what space-time looks like at the Planck scale, except even more extreme, even more violent. The physicist John Wheeler, one of the great minds of 20th century physics, and a man who had an extraordinary gift for finding vivid metaphors to describe abstract concepts, gave this phenomenon a memorable and evocative name. He called it quantum foam. The term captures perfectly the sense of turbulent, frothy chaos that characterizes reality at its smallest scales. In this foam, in this seething cauldron of quantum activity, the very geometry of the universe is constantly twisting, stretching, tearing apart, and collapsing back on itself. Virtual particles pop into existence out of nothingness, borrow energy from the vacuum for brief instants, and then vanish again. Tiny wormholes might open and close. Miniature black holes might form and evaporate in times so short that they can never be directly observed. The familiar, comfortable ideas of distance and duration, of here and there, of before and after, of cause and effect, these concepts simply stop making sense. They lose their meaning entirely, dissolving into quantum uncertainty. To actually reach this scale experimentally, to probe the Planck length with a real instrument, we would need energies in the neighborhood of 10 to the 19th power giga-electron volts. That is a level of energy, some 15 orders of magnitude, 15 powers of 10, beyond anything the Large Hadron Collider can achieve. And the Large Hadron Collider is already the most powerful particle accelerator ever built by human civilization. Even if we somehow mustered the resources and technology to construct a particle accelerator the size of our entire galaxy, spanning hundreds of thousands of light years, it still would not be enough energy to probe the Planck scale directly. Nature, it seems, has built a formidable safety barrier, an impenetrable wall, around her most secret and fundamental code, around the deepest rules that govern reality. And this barrier is not merely a technological limit, not simply a matter of building bigger machines or inventing cleverer tools. It is a physical limit, a fundamental boundary woven into the laws of nature themselves. The Planck length acts as a universal boundary, the smallest possible unit of measurement that has any physical meaning whatsoever. Below it, beneath that scale, the very concepts of space and time lose their definition. They dissolve into something else, something we do not yet understand. It is the frontier where quantum mechanics, the physics of the very small, and general relativity, Einstein's theory of gravity and space-time, collide head-on in violent disagreement. It is the place where a new unified theory of reality, a theory that reconciles quantum mechanics and gravity, must someday emerge if we are ever to understand the true nature of the cosmos. Consider this remarkable parallel. The NASA James Webb Space Telescope, that magnificent instrument now orbiting in the darkness beyond Earth, lets us look backward through time. It allows us to see galaxies as they existed more than 13 billion years ago, when the universe was still young and stars were just beginning to light up the primordial darkness. But when we turn our gaze inward instead of outward, when we look into the microscopic structure of matter instead of the vast expanses of space, we are also traveling through time. We are just traveling in the opposite direction, backward toward the moment of creation. Each deeper level we uncover, each smaller scale we manage to probe, brings us closer to the physics that governed the universe's very first moments. At nuclear scales, when we study the forces binding protons and neutrons together, we see echoes of the universe as it was in the first few seconds after the Big Bang. At the level of quarks, those fundamental particles that make up protons and neutrons, we are touching the physics that dominated in the first microseconds after creation, when the universe was unimaginably hot and dense. And at the Planck length, at that ultimate scale of distance, we meet the very instant when space-time itself came into being, when the fabric of reality first emerged from whatever existed before, if the word before even has meaning in that context. So what happens if we try to zoom in beyond that ultimate boundary? If we push past the Planck length, what do we find? Does space dissolve completely into chaos, into random, meaningless fluctuations? Or does it reveal an even deeper layer of order, a more fundamental structure that our current theories simply cannot yet describe or even imagine? Physicists, from Einstein to Stephen Hawking, from the early 20th century to today, have spent their entire lives wrestling with precisely that question. As John Wheeler once eloquently expressed it, at the Planck scale, the smooth, continuous fabric of space-time that we experience in our daily lives gives way entirely to a quantum foam of subatomic turbulence. Everything we thought was solid becomes a churning sea of possibility. For now, in our current state of technology and understanding, we cannot reach the Planck scale. We cannot perform experiments there. But the Planck length stands before us as both a wall and a doorway. It is simultaneously the boundary of everything we currently know and understand, and a tantalizing hint that something far greater, something more profound, waits patiently on the other side, just beyond our reach. And so, when we try to zoom into infinity, when we attempt to see everything there is to see, the universe does not give us a simple answer. Instead, it gives us silence. It draws a horizon using its own fundamental laws, a boundary we cannot cross. But if light itself, the messenger we have relied upon for all of human history, cannot show us the smallest truths of nature, what if something else can? Part 2. Why light cannot see atoms, but electrons can. If light is the primary way we see and understand the world around us, why does it fail so completely when we try to observe the building blocks of matter? Why is light unable to reveal the structure of an atom, while a carefully aimed beam of electrons can show us remarkable detail? At first, this sounds almost impossible, perhaps even contradictory. We imagine light as the ultimate messenger of truth, as the faithful carrier of every image we have ever known throughout human history. From the soft glow of distant galaxies, billions of light years away, to the delicate reflection dancing on the surface of a single drop of water, light brings us the universe. It carries information across vast distances, painting pictures on our retinas, allowing us to see. And yet, when scientists first tried to use ordinary light to peer into the interior structure of atoms, they found absolutely nothing. The atoms remained invisible, hidden, impossible to resolve. The problem, it turns out, is not in our instruments at all. It is not a question of building better microscopes with more perfect lenses, or grinding glass with greater precision, or using more sophisticated detection methods. The problem lies in the fundamental, inescapable nature of light itself, in the way light behaves as it travels through space from one place to another. Every ray of light, every individual photon traveling through the vacuum of space, behaves like a wave. It oscillates up and down, it ripples outward from its source, it spreads as it moves forward. This wave nature of light has been known for centuries, confirmed by countless experiments showing interference patterns and diffraction effects. And here is the crucial point that determines everything that follows. A wave simply cannot reveal fine details, cannot detect small structures that are smaller than the wave's own wavelength. This is not a technical limitation that we might overcome with clever engineering. It is not a problem that more funding or better equipment could solve. It is a fundamental law of physics, woven into the very mathematics of how waves propagate and interact with matter. This limitation appears in the equations that describe waves, in the principles of diffraction and interference. There is no loophole, no workaround. The wave nature of light imposes an absolute limit on what light can reveal. The visible light that reaches our human eyes every day, that allows us to see colours and shapes and the faces of people we love, has wavelengths measuring around half a micrometer. To put that in more familiar units, that is the same as 500 nanometers, or 500 billionths of a meter. It sounds incredibly small, and compared to everyday objects, it is. But atoms, those fundamental building blocks of all matter, of everything we can touch and see, are only about 1/10 of a nanometer across, sometimes even smaller depending on the element. They are approximately 5,000 times smaller than the wavelength of visible light, 5,000 times smaller. That is an enormous difference, a vast gulf in scale. So when we shine ordinary visible light onto a collection of atoms, it is somewhat like trying to read the fine print at the bottom of a legal document by using massive waves in a swimming pool. The ripples in the water are simply too large, too broad, to detect the tiny details of individual letters. The waves wash over the fine structure without interacting with it, without carrying any information back to us about what is there. They pass right by, oblivious to the presence of objects much smaller than themselves. To see something as small as an atom, to truly resolve its structure, we need a wave that is much, much shorter. We need something with finer ripples, with smaller crests and troughs, with a wavelength that approaches the size of what we are trying to observe. One might naturally think, then, that we should simply use higher energy light, such as X-rays or gamma rays. And that thought is partly correct, partially on the right track. X-rays, with their much shorter wavelengths, can indeed see structures far smaller than visible light can detect. X-ray crystallography, the technique of bouncing X-rays off crystals, has revealed the atomic structure of countless molecules, including the famous double helix of DNA. But even X-rays have their limits. Even they cannot reach down to the very smallest scales we wish to explore. And there is another approach, a different path, one that turned out to be remarkably powerful. That approach involves using electrons instead of photons. Now, this might seem strange at first. We typically think of electrons as particles, as tiny bits of matter with mass and charge. But in the 1920s, physicists made one of the most profound discoveries in the history of science. They realized that electrons, and indeed all matter, have a dual nature. Particles are also waves. An electron is not just a particle. It also possesses a wave associated with it, a quantum wave that guides its behavior. This wave-particle duality is at the very heart of quantum mechanics. And here is the beautiful part. The wavelength associated with an electron depends on how fast it is moving. The faster the electron travels, the more energy it carries, and the shorter its wavelength becomes. This relationship is described by the de Broglie equation, named after the French physicist Louis de Broglie, who first proposed this revolutionary idea. By accelerating electrons to high speeds, by giving them enormous amounts of kinetic energy, we can make their associated wavelengths incredibly short, far shorter than the wavelength of any light we could produce. The relationship is precise and beautiful. As the energy of an electron increases, its wavelength decreases in inverse proportion. Double the energy and you halve the wavelength. Increase the energy by 1,000 and the wavelength shrinks by 1,000. This gives us exquisite control over the scale of features we can observe. And those fast-moving, short-wavelength electrons can then be used as probes to explore the atomic and subatomic world with remarkable precision. This is the fundamental principle behind the electron microscope, one of the most important and revolutionary scientific instruments ever invented. Ernst Ruska, that German physicist we mentioned earlier, won the Nobel Prize in Physics in 1986, more than half a century after his original invention, for his development of the electron microscope back in 1931. The delay between invention and recognition was unusual, but it reflected how long it took for the scientific community to fully appreciate the profound impact of this technology. His invention opened up an entirely new realm of observation, a window into worlds that had been completely invisible before. It allowed scientists to see viruses for the first time, those tiny packages of genetic material that sit on the boundary between living and non-living. It enabled them to image the internal structure of cells, revealing organelles and membranes and molecular machines at work. It let them observe materials at the molecular level, watching atoms arrange themselves into crystal lattices, seeing defects and imperfections that determine how materials behave. The electron microscope revolutionized biology, chemistry, materials science, and medicine. It made possible countless discoveries that would have been unthinkable with optical microscopes alone. But electrons offered even more than that. At the Stanford Linear Accelerator, when physicists fired extremely high-energy electrons at protons, they were using those electrons as incredibly precise probes, as tiny, fast-moving projectiles that could interact with the quarks inside the protons. The scattering patterns, the directions in which the electrons bounced away after colliding with the protons, contained detailed information about the proton's internal structure. It was like using incredibly small billiard balls to map out an even smaller target. This technique, called deep inelastic scattering, revealed that protons and neutrons are not fundamental particles at all. They are composite objects made up of quarks bound together by the strong nuclear force. So, the answer to our question becomes clear. Light cannot see atoms because its wavelength is too large. The waves simply cannot resolve features smaller than themselves. But electrons, when given enough energy, when accelerated to sufficient speeds, can have wavelengths far shorter than atoms. They become precision tools for exploring the microscopic frontier, and this same principle applies all the way down. To see smaller and smaller structures, we must use higher and higher energies, whether we are using photons or electrons or any other particle. There is no escape from this rule. It is fundamental to the nature of waves and measurement. And yet, as we push to higher and higher energies, as we try to see deeper and deeper into the structure of matter, we run headlong into the problem we discussed before. At some point, the energy we are using to probe reality becomes so concentrated that it begins to warp space-time itself. The act of observation starts to interfere with what we are observing, not just in the quantum mechanical sense of disturbing a particle's state, but in a much more dramatic way. The energy creates gravity, and if we push far enough, if we try to probe distances as small as the Planck length, we create so much gravitational curvature that a black hole forms. Our measuring tool becomes our own worst enemy, collapsing the very space we are trying to explore. This is the ultimate irony of observation at the smallest scales. To see smaller, we need more energy, but more energy curbs space. And eventually, too much energy curbs space so drastically that nothing, not even information, can escape. The universe has built a natural limit into the act of measurement itself. It is not that our technology is insufficient, though it certainly is. It is that the laws of physics themselves forbid us from seeing beyond a certain scale. The Planck length is not just a technical barrier. It is a conceptual one, marking the boundary where our very notions of space, time, and measurement break down completely. And so we find ourselves in a curious position. We have learned to see atoms using electrons. We have learned to see inside protons using high-energy collisions. But there is a final frontier we cannot cross, a limit where the tools of observation destroy the possibility of observation. Beyond that limit lies quantum gravity, a realm where space and time themselves become uncertain, where the smooth geometry we rely upon dissolves into something we do not yet understand. Part 3. The quantum realm and the limits of certainty. To truly understand why the Planck length represents such a profound boundary, we must journey into one of the most beautiful and strange aspects of quantum mechanics. This is the principle that says the universe itself contains fundamental uncertainty, not because our instruments are imperfect, not because we lack knowledge, but because certainty itself has limits written into the laws of nature. This principle was first articulated by Werner Heisenberg in 1927, and it changed our understanding of reality forever. We call it the Heisenberg uncertainty principle, and it tells us something deeply unsettling and profoundly true. The uncertainty principle states that there are pairs of properties in nature, pairs of physical quantities, that cannot both be known with perfect precision at the same time, no matter how carefully we measure, no matter how sophisticated our instruments become. The most famous example, the one that appears in every quantum mechanics textbook, involves position and momentum. If you measure the position of a particle with great precision, with high certainty about exactly where it is in space, then the particle's momentum, which is its mass times its velocity, becomes correspondingly uncertain. You lose information about how fast the particle is moving and in what direction. The more precisely you know where the particle is located, pinpointing its position to within a tiny region of space, the less precisely you can know how fast it is moving or in what direction it will go next. Conversely, if you measure the momentum very precisely, if you know exactly how fast the particle is moving and in exactly what direction, then its position becomes fuzzy and uncertain. You cannot say precisely where it is, only that it is somewhere within a broader region. And this is not because your measurement disturbs the particle, though disturbance does play a role. It is because, at a deep and fundamental level, the particle does not actually have both properties defined with perfect precision simultaneously. This is not a limitation of what we can know. It is a limitation of what exists to be known. The universe itself does not allow both properties to have definite values at the same time. The wave function, describing the particle, the mathematical object that contains all possible information about its quantum state, simply cannot be localized sharply in both position and momentum space at once. It is mathematically impossible, forbidden by the structure of quantum mechanics itself. This is one of the most profound and startling discoveries in all of physics, and it continues to challenge our intuitions about reality even a century after its discovery. This has a direct consequence for attempts to measure very small distances. Suppose you want to measure the position of a particle with extreme precision to pin down exactly where it is in space. To do that, you need to interact with it somehow. You might bounce a photon off it, for example, and detect where the photon goes. But to measure position accurately, to get a sharp, precise reading, you need to use a photon with a very short wavelength. And a short wavelength means high energy. So far, this makes sense. This is the same rule we have been discussing all along. To see smaller, use higher energy. But here is where quantum mechanics adds a twist. When that high energy photon strikes the particle, it transfers some of its momentum to the particle. The particle recoils, its velocity changes, and suddenly its momentum becomes uncertain. The more energy you use to measure position precisely, the more you disturb the momentum. There is an unavoidable trade-off built into the fabric of reality. You cannot have perfect knowledge of both. The product of the uncertainty in position and the uncertainty in momentum is always greater than or equal to a fundamental constant, Planck's constant divided by 2. This is not a statement about technology. It is a statement about the universe. Now, for a long time, physicists thought this uncertainty principle was purely a quantum mechanical phenomenon, unrelated to gravity. But in recent decades, as physicists have tried to understand quantum gravity, they have realized something profound. When you include gravity in the picture, when you account for the fact that energy itself curves space-time, the uncertainty principle takes on a new form. It becomes what is called the generalized uncertainty principle, and it reveals something astonishing. In standard quantum mechanics, if you want to measure position more precisely, you just use more energy. There is no lower limit to how accurately you can measure position, in principle. The only limit is technological, but when you add gravity, this changes. As you use more and more energy to probe smaller and smaller distances, the energy itself starts to create a gravitational field. That field curves space-time around the region you are trying to measure, and curvature introduces a new form of uncertainty. The space you are trying to measure becomes fuzzy because the geometry itself is fluctuating. At some point, adding more energy to improve your position measurement actually makes the measurement less precise because the gravitational effects become dominant. There is a sweet spot, an optimal energy, beyond which further precision is impossible. That sweet spot occurs right around the Planck scale. The generalized uncertainty principle tells us that there is a minimum length scale in nature, approximately the Planck length, below which the very concept of distance ceases to have well-defined meaning. You cannot measure distances shorter than the Planck length because the universe itself does not define positions with greater precision than that. It is not that tiny rulers would be hard to build, it is that tiny rulers make no sense. Space itself becomes granular, discontinuous, foamy at that scale. This realization is one of the most profound in all of theoretical physics. It tells us that space is not infinitely divisible. You cannot zoom in forever. There is a smallest meaningful distance, just as there is a smallest meaningful time interval, the Planck time. Below these scales, the concepts of space and time dissolve. They are replaced by something else, something quantum, something we are still struggling to understand. Two completely different lines of reasoning, one from gravity and black hole formation, one from quantum mechanics and the uncertainty principle, lead to the same conclusion. They both point to the Planck scale as a fundamental boundary. This convergence is not a coincidence. It suggests that there is a deep unity underlying the laws of nature, a unity we have not yet fully grasped. General relativity and quantum mechanics, those two great pillars of 20th century physics, seem to be telling us the same thing in different languages. There is a scale at which they must merge, at which a new theory must take over, a theory of quantum gravity that treats space-time and quantum fields as different aspects of the same fundamental reality. This is the great quest of modern theoretical physics. We know general relativity works beautifully at large scales, describing planets, stars, galaxies, the expansion of the universe. We know quantum mechanics works beautifully at small scales, describing atoms, molecules, particles, radiation. But we do not yet have a complete theory that works everywhere, that unifies gravity and quantum mechanics into a single coherent framework. The Planck scale is where that theory must live. It is the meeting point, the boundary, the frontier. Many brilliant minds have devoted their lives to finding this unified theory. There are several candidate approaches, several mathematical frameworks that might, just might, hold the key. Two of the most well-developed are string theory and loop quantum gravity. Each takes a very different approach, yet each points toward the same basic idea, that spacetime is not fundamental, but emergent, arising from something deeper. String theory proposes that the fundamental constituents of the universe are not point-like particles, but rather tiny, vibrating filaments of energy. These strings are incredibly small, roughly the size of the Planck length. They vibrate in different patterns, and each pattern corresponds to a different particle. An electron is one vibration, a photon another, a quark yet another. Even gravity arises from the vibrations of strings. This is a beautiful idea because it naturally incorporates gravity into a quantum framework. The strings do not allow infinite sharpness or infinite energy density. When you try to pack energy into a small region, the strings simply stretch and oscillate. They never collapse into mathematical points. This avoids many of the infinities that plague other attempts to combine quantum mechanics and gravity. Loop quantum gravity takes a completely different approach. Instead of starting with strings moving through spacetime, it starts with spacetime itself. It asks, what if space is not continuous but discrete? What if geometry is quantized, built from fundamental, indivisible units? In loop quantum gravity, space is made of loops and nodes, woven together into a structure called a spin network. Each loop represents a quantum of area, each node a quantum of volume. These quanta are roughly Planck-sized. Space, in this view, is not a smooth fabric, but a granular, network-like structure at the smallest scales. Time is also quantized, ticking forward in discrete Planck time intervals. This is a radical reimagining of reality, yet it emerges naturally from trying to apply quantum principles to Einstein's equations. Both string theory and loop quantum gravity, despite their differences, point toward the same profound conclusion. Space and time are not fundamental entities. They are not the stage upon which the universe performs. Instead, they are emergent properties, byproducts of deeper relationships and interactions. The smooth space-time we experience in our everyday lives, the stage on which planets orbit and light travels, is a kind of approximation, a macroscopic average over countless microscopic quantum processes. It is like the surface of a lake appearing smooth and glassy from a distance, even though up close it is made of individual water molecules bouncing and jostling chaotically. This idea, that space-time is emergent, is one of the most revolutionary in all of physics. It suggests that the questions we ask, the questions about what happens at a point in space or an instant in time, are the wrong questions to ask at the Planck scale. There are no points, there are no instants. There is only the network of relationships, the web of quantum connections from which our familiar notions of geometry arise. At microscopic scales, at the scales of galaxies, planets, oceans, even atoms, this emergent spacetime works perfectly. It is smooth, continuous, predictable. GPS satellites depend on it. Light follows geodesics through it. NASA spacecraft navigate using it with astonishing accuracy, but zoom far enough down, probe deeply enough, and the approximation breaks. The coordinates that guide rockets and photons begin to dissolve. At the Planck scale, a ruler has no meaning, a clock ticks no time. The universe is no longer here or there, no longer now or then. It is a web of quantum interactions, a network of possibilities flickering between potential states. It is a strange and wondrous place to imagine, almost impossible to visualize. Yet it might be the birthplace of everything we see. The laws that shaped the first instant after the Big Bang, the forces that drove the inflation of space, the processes that formed matter, the seeds from which galaxies grew, all of these trace back to this regime where geometry itself was quantum, where space and time were not yet smooth and continuous, but discrete and uncertain. Our great observatories, the NASA Wilkinson Microwave Anisotropy Probe, the European Space Agency's Planck satellite, and now the James Webb Space Telescope, have pushed our observational limits ever closer to the beginning of time. They can see the universe as it was just hundreds of millions of years after the Big Bang, when the first stars lit up the primordial darkness, when galaxies first began to coalesce from clouds of hydrogen and helium. But the true origin, the quantum moment when space-time itself was born, when the universe was smaller than an atom and hotter than we can imagine, remains hidden behind the natural wall of uncertainty. We cannot see back to the Planck time because the very concepts of seeing and back cease to apply. The physicist Carl Sagan once said something beautiful. He said, "We are a way for the cosmos to know itself." But now it seems the cosmos has drawn a boundary around its own reflection. We can observe the stars and galaxies. We can trace the curvature of space-time across billions of light years. We can measure the cosmic microwave background radiation, that faint glow left over from the Big Bang. But beyond a certain precision, beyond a certain depth, nature refuses to be seen. Not out of stubbornness, not as a challenge, but simply because vision itself has meaning only within the realm of smooth space-time. And at the Planck scale, smooth space-time does not exist. This is not a dead end. It is not a failure. It is an invitation, a call to think differently. If distance itself is only an approximation, if space and time are emergent rather than fundamental, then physics must find a language deeper than geometry. It must develop a theory not of where things are or when things happen, but of how things relate, how information is shared, how quantum states become entangled. In some versions of quantum gravity, particularly those inspired by black hole physics and the holographic principle, this is exactly what happens. Space, in these revolutionary theories, emerges from quantum entanglement in a way that would have seemed like pure fantasy just a few decades ago. Entanglement is a phenomenon first recognized in the early days of quantum mechanics, where two or more particles share a quantum state in such an intimate way that they become parts of a single quantum system. They are connected by invisible threads of correlation that persist no matter how far apart they are separated in space. When you measure one entangled particle, determining some property like its spin direction, the other particle instantly, faster than any signal could travel, takes on a corresponding state. If one is measured to be spinning up, the other is found to be spinning down, or vice versa. The measurement on one particle instantly affects the state of the other, no matter whether they are separated by millimeters or by billions of light years. Einstein famously called this phenomenon spooky action at a distance, and he was deeply uncomfortable with it. He believed it violated the principle of locality, the idea that objects should only be influenced by their immediate surroundings, not by events happening far away. Einstein spent years trying to show that entanglement was not real, that it was an artifact of incomplete theory or faulty reasoning. He proposed thought experiments meant to demonstrate that quantum mechanics must be missing something, that there must be hidden variables determining outcomes in a way that preserved locality. But he was wrong, though his concerns were sincere and his arguments were sophisticated. Experiments have confirmed over and over and over again that entanglement is absolutely real, not an illusion or a measurement artifact. It is a fundamental feature of quantum mechanics, one of the strangest and most profound aspects of how nature actually works at the deepest level. Physicists have entangled photons, electrons, atoms, even microscopic diamonds. They have demonstrated entanglement over distances of hundreds of kilometers. The phenomenon is now routinely used in quantum cryptography and is the basis for emerging quantum computing technologies. Recent research suggests that entanglement might be more than just a curious quantum phenomenon. It might be the very fabric from which space itself is woven. In this view, when two regions of space are highly entangled, they are close together. When they are less entangled, they are farther apart. Distance is not a property of space. It is an effect of entanglement. Space exists because quantum information is shared. Without interaction, without entanglement, there is no geometry, no distance, no between, The very structure of space arises from the way quantum systems correlate with one another. It is a breathtaking thought, almost mystical in its beauty. At the deepest level, reality may not be made of things, but of relationships. The universe is not a container filled with objects. It is a network of connections, a web of interactions. Space is not a place but a process, constantly being woven and rewoven by the exchange of quantum information. Distance is the manifestation of correlation. Time is the unfolding of entanglement. These ideas are still speculative, still in development. They are maps drawn at the edge of knowledge, beautiful and self-consistent in their mathematics, but waiting for experimental data to confirm or refute them. And that is where the great observatories of the future may help. By measuring gravitational waves with extreme precision, by detecting tiny fluctuations in spacetime as it ripples from distant cosmic events, we might glimpse signatures of quantum geometry. The Laser Interferometer Space Antenna, LISA, scheduled for launch in the coming decades, will listen for gravitational waves from sources across the universe. The Einstein telescope, a proposed ground-based detector far more sensitive than anything we have today, will measure spacetime vibrations with unprecedented accuracy. If space is granular at the Planck scale, if it is made of discrete quanta of geometry, then gravitational waves travelling across billions of light-years might accumulate tiny errors, small deviations from what general relativity predicts. Detecting those deviations would be the first direct evidence of quantum gravity, the first experimental glimpse beyond the smooth space-time of Einstein's theory. The stakes are enormous, almost unimaginable. If we can detect signatures of quantum geometry, if we can find evidence that space itself is quantized, we will have confirmed one of the deepest ideas in theoretical physics. We will have shown that reality, at its most fundamental level, is discrete and quantum, not continuous and classical. It would be a revolution as profound as the shift from Newton's physics to Einstein's, as dramatic as the birth of quantum mechanics in the early 20th century. But even if that day is far away, even if decades or centuries pass before we have the technology and understanding to test these ideas, one truth already stands clear before us. The closer we look, the less we see. Not because the universe is hiding its secrets out of malice or caprice, but because the tools we use, the very concepts of space and time and measurement, begin to melt and dissolve when pushed to their limits. They are useful approximations, powerful frameworks that work brilliantly at everyday scales, and even at extreme scales of galaxies and atoms. But they are not the final truth. They are not the deepest layer. At the Planck scale, distance is not wrong. It is incomplete, like a useful word in a language that breaks down when the conversation goes too deep, when we try to express ideas the language was never designed to handle. What lies beyond the Planck scale may not be smaller or larger. It may be different, orthogonal to our familiar notions of size and position. It may be a realm described not by meters and seconds, but by quantum information, by entanglement entropy, by degrees of freedom we have not yet learned to count. The theoretical physicist Nima Arkani Hamed, one of the leading thinkers in modern physics, has put it bluntly. He says space-time is doomed. He does not mean it will vanish, that the universe will collapse or cease to exist. He means that space-time is only a shadow, an emergent approximation of a richer, deeper quantum foundation. Just as temperature is an emergent property of molecular motion, not a fundamental thing in itself, space-time might be an emergent property of quantum entanglement, of information woven into patterns we call geometry. This is a stunning idea. It suggests that the most fundamental description of reality will not mention space or time at all. It will describe something else, something from which space and time naturally arise when you look at the system from a certain perspective in a certain limit. And so, after all our measurements and equations, after centuries of refining our understanding of the cosmos, physics arrives back at wonder. We stand before a universe where and when are not the final truths. They are patterns, useful patterns, patterns that emerge from something deeper and more fundamental, something still unnamed, something we are only beginning to glimpse. The smooth space-time of Einstein's relativity is real and accurate in its domain, just as Newton's laws are real and accurate in theirs. But it is not the whole story. Beneath it lies a quantum realm, a realm of networks and entanglement, a realm where the universe is woven from relationships rather than built from objects. This is the frontier of human knowledge today. It is a beautiful, mysterious place. And it invites us not just to calculate and measure, but to reimagine what we mean by existence itself. Part 4: Energy, Gravity, and the Formation of Black Holes. Let us now explore in greater detail exactly what happens when we concentrate energy into smaller and smaller regions of space. This is one of the most fascinating aspects of the story, and it ties together quantum mechanics, general relativity, and the ultimate limits of observation in a profound way. We have said that to see smaller, you must use higher energy. But why exactly does higher energy lead to gravitational collapse? Why does the act of measurement, pushed to its extreme, create a black hole? To answer these questions, we need to understand how energy and space-time interact, how they shape each other. Einstein's general theory of relativity, published in 1915, fundamentally changed our understanding of gravity. Before Einstein, gravity was thought of as a force, an invisible pulling between masses. Newton's law said that every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This law worked beautifully for centuries, predicting planetary orbits, the motion of comets, the tides of Earth's oceans. But it had a problem. It assumed that gravity acted instantaneously across any distance, that if the sun suddenly vanished, Earth would fly off course immediately with no delay. This violated the principles of relativity, which said that no information can travel faster than light. Einstein resolved this paradox with a radical new idea. Gravity is not a force, it is the curvature of spacetime itself. Mass and energy tell spacetime how to curve, and curved spacetime tells mass and energy how to move. A planet orbiting a star is not being pulled by an invisible force. It is following the straightest possible path through curved spacetime, a path we call a geodesic. The star's mass warps the fabric of space and time around it, creating a depression, a valley in the geometry. The planet rolls along the sides of that valley, and we perceive its motion as an orbit. This is a beautiful picture, and it leads to many predictions that have been confirmed by experiment. General relativity predicts that light bends when passing near a massive object, and we have observed this bending, called gravitational lensing, countless times. It predicts that time runs slower in strong gravitational fields, and this has been measured with atomic clocks. It predicts the existence of gravitational waves, ripples in spacetime produced by accelerating masses, and we have detected these waves directly using interferometers like LIGO and Virgo. General relativity is one of the most successful theories in all of physics, tested again and again in extreme conditions, from the surface of neutron stars to the edge of black holes. But general relativity also makes a strange and dramatic prediction. If you compress enough mass or energy into a small enough region, the curvature of spacetime becomes so extreme that it closes off entirely. A boundary forms, called an event horizon, beyond which nothing can escape, not even light. This is a black hole, one of the most exotic and fascinating objects in the universe. Black holes are real. We have observed them, measured their masses, even photographed the glowing gas swirling around them. The supermassive black hole at the center of our galaxy, called Sagittarius, a star, has a mass of about 4 million suns, and it lurks in the heart of the Milky Way, invisible itself but revealed by the orbits of stars circling it at tremendous speeds. Now, here is the key insight. The formation of a black hole is not just about mass, it is about energy density, the amount of energy packed into a given volume of space. According to relativity, mass and energy are equivalent. The famous equation E = mc² tells us that mass is just a very concentrated form of energy. So concentrating energy into a small region is equivalent to concentrating mass. And if you concentrate enough energy or mass into a small enough volume, you reach a critical threshold, a point where the escape velocity exceeds the speed of light. At that moment, an event horizon forms and a black hole is born. This has profound implications for our attempts to probe smaller and smaller distances. When we fire a high-energy particle at a target, when we use that particle as a probe to measure tiny structures, we are concentrating energy into a small region. The higher the energy, the smaller the region we can probe, because the wavelength of the particle becomes shorter. But at some point, if we make the energy high enough, we concentrate so much energy into such a small volume that the region itself collapses into a black hole. We have crossed the threshold. The gravitational field has become so strong that space-time curves back on itself, sealing off the interior from the outside universe. When this happens, our attempt to measure has failed catastrophically. We wanted to see smaller, to probe deeper, but instead we have created an impenetrable barrier. No information can escape from inside the event horizon. No signal, no light, no particle can carry back data about what is happening in that region. The measurement has destroyed the measurability. The observer has become the observed, swallowed by the very phenomenon it was trying to study. Physicists have calculated the energy required for this to happen, the threshold where measurement becomes impossible. It turns out to be exactly the energy associated with the Planck scale. If you try to probe a region smaller than the Planck length, roughly 1.6 times 10 to the negative 35 meters, you need to use a particle with energy around the Planck energy, about 10 to the 19th giga-electron volts. And when you concentrate that much energy into a region that small, the gravitational field becomes so intense that a black hole forms. The Planck length is the Schwarzschild radius, the size of the event horizon, for a black hole with one Planck mass. It is the point where quantum mechanics and general relativity meet head-on, where neither theory can be ignored, where both are essential. This is why the Planck scale is so special. It is not an arbitrary boundary drawn by physicists. It emerges naturally from the interplay of quantum mechanics, which governs the very small, and general relativity, which governs gravity and space-time. Two completely independent theories, developed to explain different phenomena, converge on the same scale. They both say, here is the limit, here is where new physics must take over. Below the Planck length, we enter a realm that is both quantum and gravitational. Space-time itself becomes uncertain, fluctuating wildly due to quantum effects. Virtual black holes might pop in and out of existence, borrowing energy from the vacuum for brief instants before annihilating. The smooth geometry we rely on dissolves into a churning foam of possibilities. Distance and duration lose their meaning. The very concepts we use to describe reality, to make measurements and predictions, break down completely. This is not science fiction. This is what our best theories tell us must happen. Of course, we cannot test it directly. We cannot build an experiment to probe the Planck scale, but the mathematics is clear and consistent. It points us toward a new understanding, a new framework, where space-time is not fundamental but emergent, where quantum mechanics and gravity are unified into a single coherent theory. Several research programs are working toward this goal. String theory, as we have mentioned, is one of the most well-developed. In string theory, particles are not points, but tiny loops of vibrating energy, and gravity arises naturally from the vibrations. The theory requires extra dimensions beyond the three of space and one of time that we experience, dimensions that are curled up so tightly that we cannot detect them at everyday scales. But at the Planck scale, these extra dimensions might become important, might reveal themselves in subtle ways. Loop quantum gravity is another approach, focusing on quantizing spacetime itself. It imagines space as a network of discrete loops, each carrying a quantum of area. Time advances in discrete ticks. This granular structure prevents infinities, avoids the singularities that plague classical general relativity. In loop quantum gravity, the Big Bang might not have been a point of infinite density, but rather a quantum bounce, a moment when the universe was compressed to Planck scale dimensions but did not collapse completely. Instead, quantum effects created a kind of repulsive pressure, causing the universe to expand again. This is a speculative idea, but it shows how quantum gravity might resolve some of the deepest puzzles in cosmology. There are other approaches as well, other frameworks being explored. Some physicists are investigating causal set theory, which treats space-time as a collection of discrete events related by causal connections. Others are studying asymptotic safety, which suggests that gravity might become well behaved at high energies due to a special kind of scale invariance. Still others are exploring the holographic principle, which says that the information contained in a volume of space can be encoded on its boundary like a hologram. This principle, inspired by the physics of black holes, suggests that our three-dimensional reality might be a projection of information living on a two-dimensional surface. All of these ideas are tentative, speculative, incomplete, but they share a common theme. They all suggest space-time is not the end of the story. It is a useful approximation, an emergent structure that arises from something more fundamental, and they all point toward the Planck scale as the boundary where this deeper structure becomes important, where the approximation breaks down and the true quantum nature of reality reveals itself. So when we ask what happens at the Planck length, the answer is not simple. It is not a matter of finding smaller particles or tinier structures. It is a matter of recognizing that our familiar concepts, space and time, are provisional, limited, applicable only in certain regimes. Beyond the Planck scale, we enter a new territory, a territory that requires new concepts, new mathematics, new ways of thinking. It is a territory we have not yet fully mapped, but whose existence we can infer from the collision of quantum mechanics and gravity. And this brings us to one of the deepest questions in all of physics. If space and time are emergent, what are they emerging from? What is the deeper substrate, the more fundamental reality? Some physicists believe it is quantum information, the abstract pattern of correlations and entanglements between quantum systems. Others think it might be something even more abstract, a structure described by pure mathematics, by symmetries in group theory, by algebraic relationships that do not depend on any notion of space or time. We do not yet know. This is the frontier, the edge of human knowledge, the place where science becomes almost indistinguishable from philosophy. But we are making progress. Every year, new ideas are proposed, new calculations are performed, new connections are found between different theories. And slowly, piece by piece, the picture is becoming clearer. We are learning that the universe is far stranger, far more subtle than we ever imagined. We are learning that the deepest truths are not about what things are made of, but about how they relate, how they interact, how information flows between them. And in that process, we are also learning something about ourselves. We are learning that the human mind, this 3-pound lump of matter inside our skulls, is capable of astonishing feats. It can contemplate the structure of space-time. It can imagine universes beyond our own. It can peer into the nature of reality itself, armed with nothing but mathematics and logic, and the courage to ask questions that have no easy answers. Part 5. The universe at the smallest scales and the quest for unification. As we have journeyed through the landscape of the very small, from atoms to quarks to the Planck length, a profound pattern has emerged. The deeper we look, the more we find that the universe is not made of stuff, but of structure, not of objects, but of relationships. This insight is at the heart of modern physics, and it points us toward the ultimate goal, a unified theory that explains all forces, all particles, all interactions within a single coherent framework. Throughout the 20th century, physics achieved a series of spectacular unifications. In the 1800s, electricity and magnetism were understood as separate phenomena. Then, in the 1860s, James Clerk Maxwell showed that they were actually two aspects of the same underlying force, electromagnetism. His equations described how electric fields and magnetic fields intertwine, how they generate each other, how they propagate through space as light. It was a triumph of theoretical physics, showing that seemingly different forces were unified at a deeper level. In the 1960s and 70s, physicists achieved another unification. They showed that electromagnetism and the weak nuclear force, the force responsible for radioactive decay, were actually two aspects of a single electroweak force. At very high energies, at temperatures like those in the early universe just after the Big Bang, electromagnetism and the weak force merge into one. This was confirmed experimentally in the 1980s with the discovery of the W and Z bosons, the particles that carry the weak force. It earned several physicists the Nobel Prize and solidified the standard model of particle physics, our current best theory of how particles and forces behave. The standard model is remarkably, almost miraculously successful, one of the crowning achievements of 20th century physics. It describes three of the four fundamental forces that govern all interactions in nature: electromagnetism, which binds electrons to nuclei and causes all of chemistry; the weak nuclear force, which is responsible for radioactive decay and plays a crucial role in how stars shine and in the formation of elements; and the strong nuclear force, the most powerful force in nature, which holds quarks together inside protons and neutrons and binds those protons and neutrons together inside atomic nuclei. It describes with mathematical precision all the known fundamental particles that make up matter and mediate forces. This includes 6 types of quarks, the building blocks of protons and neutrons, which come in whimsically named varieties: up, down, strange, charm, top and bottom. It includes 6 types of leptons, a category that includes the familiar electron as well as its heavier cousins, the muon and tau, plus 3 types of nearly massless, ghostly neutrinos that pass through matter almost without interacting. And it includes the force-carrying bosons, the photon that carries electromagnetism, the gluons that carry the strong force, the W and Z bosons that carry the weak force, and the recently discovered Higgs boson that gives other particles their mass. The standard model has been tested in literally thousands upon thousands of experiments over the past 50 years, from particle colliders smashing protons together at enormous energies to delicate measurements of atomic spectra to observations of particle decays. Every single test, without exception, has confirmed its predictions with astonishing precision. Some quantities have been calculated and measured to agreement within 1 part in a billion or better. The discovery of the Higgs boson in 2012 at the Large Hadron Collider in Switzerland was the final missing piece of the puzzle, confirming the mechanism that gives particles their mass through their interaction with a field permeating all of space. It was a triumph decades in the making, the culmination of theoretical work dating back to the 1960s and experimental work requiring the construction of the most complex machine ever built by human civilization. But the standard model is incomplete. It does not include gravity. Einstein's general relativity describes gravity beautifully at large scales, but it is a classical theory, not a quantum one. Attempts to quantize gravity using the same methods that worked for the other forces run into severe difficulties. Calculations produce infinities that cannot be removed. The theory becomes mathematically inconsistent. This is the central problem of modern physics: how to unite quantum mechanics and general relativity, how to describe gravity at the quantum level. The Planck scale is where this unification must occur. At everyday scales, gravity is incredibly weak compared to the other forces. The electromagnetic force holding your body together is vastly stronger than the gravitational pull of the entire Earth. But as you concentrate energy into smaller regions, gravity grows rapidly in importance. At the Planck scale, gravity becomes just as strong as the other forces. It can no longer be ignored or treated as a small perturbation. Quantum mechanics and general relativity become equally important, and neither can be neglected. This is why the Planck length is not just a technical curiosity. It marks the energy scale where all 4 forces, electromagnetism, the weak force, the strong force, and gravity, should be described by a single unified theory. Physicists call this the theory of everything, though that is a somewhat grandiose name. It would not explain everything about the universe, but it would explain the fundamental rules, the basic laws from which everything else emerges. Finding this theory has been one of the great quests of physics for nearly a century. Einstein spent the last 30 years of his life searching for a unified field theory, trying to merge gravity and electromagnetism. he did not succeed, partly because the other forces had not yet been discovered, partly because the tools of quantum field theory were not yet fully developed. But his dream lives on, pursued by thousands of physicists around the world. String theory is perhaps the most famous, most widely discussed, and most mathematically developed candidate for a theory of quantum gravity. It emerged in the late 1960s, originally as an attempt to describe the strong nuclear force that binds quarks together inside protons and neutrons. But it was soon realized that it naturally included gravity in a way that no one had anticipated. In string theory, the fundamental objects underlying all of reality are not point particles, but one-dimensional strings, incredibly tiny filaments of energy, vibrating loops or segments that oscillate in complex patterns. These strings are so small that at everyday scales, or even at the scales we can probe with our most powerful particle accelerators, they would appear as points. We cannot see their extended structure directly. Different vibrations, different patterns of oscillation, correspond to different particles that we observe in nature. A string vibrating in one particular way, with one frequency and mode, looks and behaves exactly like an electron. The same string vibrating in a different way, with a different frequency, looks like a photon, the particle of light. Yet another vibrational pattern produces a quark, and so on. Every particle in the standard model corresponds to a different vibrational mode of these fundamental strings. It is a beautiful, unifying idea, suggesting that all the diversity of particles we see, all the different types of matter and force carriers, are actually the same thing at the deepest level, just strings vibrating in different ways, like different notes played on the same violin string. Remarkably, and this was the breakthrough that transformed string theory from an interesting curiosity into a serious candidate for quantum gravity, one of the possible vibrations corresponds exactly to the graviton, the hypothetical quantum particle that carries the gravitational force, that mediates gravity in the same way that photons mediate electromagnetism. Gravity is built into string theory from the very start. It is not added by hand as an afterthought. It arises naturally, inevitably, from the mathematics of vibrating strings. This was stunning because all previous attempts to include gravity in a quantum framework had failed, producing infinities and inconsistencies. But string theory, because it replaces point particles with extended objects, avoids these problems. Strings cannot be squeezed into infinitesimally small regions. They have a finite size, roughly the Planck length, and this finite size smooths out the mathematical singularities that plagued other theories. String theory has some beautiful features. It avoids the infinities that plague other attempts to quantize gravity. It predicts the existence of extra dimensions beyond the four we experience, and these extra dimensions might explain why gravity is so much weaker than the other forces. It connects to many areas of mathematics, from topology to algebraic geometry, and has inspired new ideas in pure mathematics as well as physics. But it also has challenges. There are many versions of string theory, many ways the extra dimensions can be compactified, and each choice leads to a different physical prediction. This landscape of possibilities contains perhaps 10 to the 500th different solutions, and we do not yet know which one, if any, describes our universe. Moreover, string theory makes predictions primarily at the Planck scale, far beyond what we can test directly. Some critics argue that it is not really physics but mathematics, a beautiful mathematical structure that may or may not correspond to reality. Loop quantum gravity takes a different philosophical approach. Instead of starting with particles moving through space-time, it starts with space-time itself and asks how to quantize it directly. The result is a picture of space as a network of loops, a quantum geometry where areas and volumes come in discrete units. Time is also discrete, advancing in tiny quantum steps. This solves some of the problems that general relativity has with singularities, points where the curvature becomes infinite. In loop quantum gravity, there are no singularities. Space cannot shrink to zero size because there is a minimum quantum of volume. The Big Bang, in this picture, might not have been a true singularity, but rather a moment when the universe was incredibly small but still finite, still describable by the laws of quantum geometry. Loop quantum gravity has its own challenges. It is less developed than string theory in some ways, and it has not yet fully incorporated the standard model of particle physics. Combining quantum geometry with the particles and forces we observe is a major ongoing effort, but it has some advantages too. It does not require extra dimensions. It is background independent, meaning it does not assume a fixed space-time structure, but derives space-time from more fundamental quantum principles. And it makes some predictions that might be testable, such as small modifications to the dispersion relation for light travelling across cosmological distances. Other approaches exist as well. Asymptotic safety suggests that gravity might be a quantum field theory after all, but one that behaves in a special way at high energies, remaining mathematically well defined. Causal dynamical triangulations attempts to construct space-time from simple building blocks, gluing together tiny simplices to form a quantum geometry. The holographic principle, inspired by black hole thermodynamics, suggests that the information in a volume of space is encoded on its surface, and that our three-dimensional universe might be a projection from a two-dimensional boundary. This principle has led to the AD-CFT correspondence, a powerful mathematical tool that relates gravity in one theory to quantum field theory in another, providing new ways to calculate and understand both. All of these approaches, despite their differences, share a common insight. Space-time is not fundamental. It emerges from something deeper, something quantum. At the Planck scale, the smooth geometry of Einstein's relativity dissolves, and a new quantum structure takes over. What that structure is exactly remains to be fully understood. But the fact that multiple independent approaches point toward the same basic conclusion gives us confidence that we are on the right track. Testing these ideas experimentally is extraordinarily, almost impossibly difficult. The Planck energy. The energy scale where quantum gravity effects become important and dominant is approximately 10 to the 19th giga-electron volts, a number so enormous it defies comprehension. To put this in perspective, the Large Hadron Collider, the most powerful particle accelerator ever constructed by human civilization, built at enormous cost in a tunnel 27 kilometers in circumference beneath the border between France and Switzerland, reaches collision energies of only about 10 to the 4th giga-electron volts. That means we would need an accelerator roughly a quadrillion times more powerful than the LHC to directly probe the Planck scale. We would need an accelerator the size of the entire solar system, or perhaps even larger, with magnets and detectors scattered across billions of kilometers. This is obviously far beyond anything we can build with current or foreseeable technology. But there are indirect ways to test quantum gravity, clever methods that might reveal its effects without needing to reach the Planck energy directly. Gravitational wave astronomy is one of the most promising avenues available to us. When black holes merge in the depths of space, when neutron stars collide and create brilliant explosions called kilonovae, they produce ripples in the fabric of space-time itself. These gravitational waves travel across the universe at exactly the speed of light, carrying information about the cataclysmic events that created them. Detectors like LIGO, the Laser Interferometer Gravitational Wave Observatory in the United States, and Virgo in Italy have already observed dozens and dozens of these spectacular events since the first historic detection in September of 2015. The detectors work by measuring tiny distortions in space-time as gravitational waves pass through Earth, distortions so small that they strain credibility. LIGO can detect changes in distance smaller than the width of a proton across its 4-kilometer-long arms. Future detectors promise even greater sensitivity. The space-based LISA mission, the Laser Interferometer Space Antenna, scheduled for launch in the 2030s, will have arms millions of kilometers long, forming a giant triangle of spacecraft floating in orbit around the Sun. The ground-based Einstein telescope, currently in the planning stages in Europe, will be far more sensitive than current detectors, able to see gravitational waves from the entire observable universe. These instruments will measure gravitational waves with such extraordinary precision that tiny deviations from the predictions of general relativity, deviations caused by quantum effects in the structure of spacetime itself, might finally become visible to human observation. Another promising avenue is cosmology, the study of the universe as a whole. The cosmic microwave background radiation, that faint glow left over from the Big Bang, carries imprints of the very early universe when it was hot and dense and quantum effects were important. By studying the patterns in this radiation, by measuring tiny fluctuations in temperature and polarization, we can learn about the physics that operated at energies far beyond what any particle accelerator can reach. Future missions, both ground-based and space-based, will map the cosmic microwave background with unprecedented precision, searching for signatures of quantum gravity, for hints of extra dimensions, for evidence of inflation and the very first moments of cosmic history. We are living in an exciting time for fundamental physics. For the first time in history, we have the mathematical tools and the observational capabilities to seriously address the question of quantum gravity. We do not yet have the final answer. We may not have it for decades or even longer. But we are making progress step by step, experiment by experiment, calculation by calculation. And as we make this progress, we are learning something profound about the nature of reality. We are learning that the universe is far more subtle than our intuitions suggest. Space and time, those seemingly solid and fundamental aspects of existence, are actually emergent, provisional, useful approximations that break down at the smallest scales. Distance and duration are not fundamental truths, but convenient descriptions that arise from deeper quantum processes, from the entanglement and interaction of quantum fields. This is a humbling realization, but also an empowering one. It tells us that the human mind is capable of reaching beyond its everyday experience, beyond the scales where evolution shaped our brains, and grasping truths about the deep structure of reality. With mathematics and logic and careful observation, we can understand things that are utterly invisible, utterly removed from direct experience. We can peer into the quantum foam, contemplate the Big Bang, imagine universes beyond our own. This is one of the most remarkable achievements of our species. And it reminds us that science is not just about building better technology or making practical applications, though those are valuable. At its core, science is about wonder, about curiosity, about the deep human desire to understand the world we find ourselves in. It is about asking questions that have no immediate practical value. Questions like, what is space made of? What happened at the beginning of time? What are the fundamental laws that govern reality? These questions may not help us build better smartphones or cure diseases, at least not directly, but they enrich our lives in a different way. They give us a sense of our place in the cosmos, a sense of connection to something larger than ourselves. As we stand here on this small planet, orbiting an ordinary star in an ordinary galaxy, looking out at a universe containing hundreds of billions of galaxies, and looking inward at the quantum fabric from which everything is woven, we realize that we are part of something vast and ancient and beautiful. We are made of atoms forged in the cores of dying stars. We are products of a universe that has been evolving for nearly 14 billion years, from a hot, dense quantum state to the rich, complex cosmos we see today. And now, in a cosmic blink of an eye, we have gained the ability to ask questions about our own origins, to contemplate the laws that brought us into being. This is what science offers us. Not certainty, not final answers, but a way of engaging with the mystery, a way of pushing against the boundaries of knowledge with humility and courage. The Planck length stands before us as one of those boundaries, a place where our current understanding reaches its limit. But it is not a wall. It is a doorway, an invitation to think more deeply, to question our assumptions, to imagine new possibilities. Part 6. The meaning of measurement at the smallest scales. We have explored the Planck length from many angles, from quantum mechanics to general relativity, from particle physics to cosmology. Now let us step back and ask a more philosophical question. What does it mean to measure something? What does it mean to say that a distance has a certain value? At everyday scales, this seems obvious. We take a ruler, place it next to an object, and read off the length. Simple. But as we have seen, measurement becomes strange and problematic at very small scales. The act of measuring interferes with what is being measured, and at the Planck scale, measurement itself becomes impossible. Let us think carefully about why this is and what it tells us about the nature of physical reality. Measurement, at its core, is an interaction. To measure the position of a particle, you must interact with it in some way. You might bounce a photon off it and detect where the photon goes. You might surround it with a detector and wait for it to trigger a signal. But no matter what method you use, measurement requires interaction, and interaction always transfers energy and momentum. This is unavoidable. It is not a limitation of our instruments, but a fundamental feature of the universe. In classical physics, the physics of Newton and Maxwell, we imagine that we can make these interactions as gentle as we like. We can use very low energy photons, very weak probes that barely disturb the system we are measuring. In principle, we can make the disturbance arbitrarily small and thus measure position and momentum simultaneously with perfect precision. But quantum mechanics tells us this is wrong. Heisenberg's uncertainty principle says there is a fundamental limit to how precisely we can know both position and momentum. The more precisely we measure one, the less precisely we can know the other. This is not because our measurement disturbs the system, though it does, but because the system does not actually have both properties defined with perfect precision at the same time. The particle does not have a definite position and a definite momentum simultaneously. It exists in a superposition, a quantum state that contains possibilities rather than certainties. When we add gravity to this picture, things become even stranger. Energy, according to general relativity, curves space-time. So when we use a high-energy photon to measure position precisely, that photon carries energy, and that energy creates a gravitational field. At low energies, this is negligible. The space-time curvature caused by a single photon is utterly insignificant. But as we push to higher and higher energies, as we try to measure smaller and smaller distances, the gravitational effects become important. The photon we use to measure position starts to curve space-time noticeably. And at some point, if we push far enough, the energy density becomes so high that space-time curves back on itself, an event horizon forms. We have created a black hole. This means that there is a fundamental limit to how precisely we can localize a measurement. If we try to measure a distance smaller than the Planck length, we must use energy greater than the Planck energy. But concentrating that much energy into such a small region creates a black hole, and the information we were trying to obtain is lost behind the event horizon. The measurement destroys itself. Observation becomes impossible. This is formalized in the generalized uncertainty principle, an extension of Heisenberg's principle that includes gravitational effects. In standard quantum mechanics, the uncertainty in position can be made arbitrarily small by using arbitrarily high energy. But in quantum gravity, this is no longer true. There is a minimum position uncertainty, roughly equal to the Planck length, below which further precision is physically meaningless. The universe simply does not define positions more precisely than that. What does this tell us about the nature of space? One interpretation is that space is fundamentally discrete, made of tiny, indivisible quanta, roughly the size of the Planck length. Space is not infinitely divisible. It is granular, like a photograph made of pixels. Zoom in far enough and you see the pixels. Zoom in on space far enough and you see the Planck scale granularity. This is the picture suggested by loop quantum gravity and some other approaches. Space has a smallest unit, a quantum of volume, and distances smaller than the Planck length simply do not exist. Another interpretation is that space is not an independent thing at all, but rather an emergent property of quantum entanglement. In this view, space does not exist at the fundamental level. What exists are quantum systems and their correlations. When two systems are highly entangled, we say they are close together in space. When they are less entangled, we say they are far apart. Distance is a measure of entanglement. Geometry emerges from the pattern of quantum correlations. This is a radical idea, but it is supported by several recent results in theoretical physics, particularly in the context of the holographic principle and the ADS-CFT correspondence. Both interpretations lead to the same basic conclusion. Space, as we understand it from everyday experience and from classical physics, is not fundamental. It is either made of discrete building blocks or it emerges from quantum entanglement. Either way, it is not the smooth, continuous manifold that Einstein assumed in his theory of general relativity. At the Planck scale, the approximation breaks down, and the true quantum nature of space reveals itself. This has profound implications for how we think about reality. For centuries, since the time of Newton, and even earlier, physics has been based on the idea that objects exist at definite positions in space and move through space over time. Space and time were the stage, the fixed background upon which the drama of physics played out. Even in general relativity, where space-time is dynamic and curved by mass and energy, it is still treated as a fundamental entity, a smooth geometric structure. But if space is not fundamental, if it emerges from something deeper, then the entire framework of physics must be rethought. We can no longer ask where a particle is or when an event happens, at least not at the Planck scale. These questions presuppose a space-time structure that does not exist at that level. We must ask different questions about quantum states, about entanglement, about information. The theory of quantum gravity, when we finally have it, will not describe particles moving through space. It will describe something else, something more abstract, from which the appearance of particles and space emerges in the appropriate limit. This is a huge conceptual shift, perhaps the biggest since the shift from classical mechanics to quantum mechanics in the early 20th century. And it is still ongoing. We do not yet have a complete theory of quantum gravity, so we do not fully understand what replaces space-time at the fundamental level. But we are beginning to see the outlines, to glimpse the structure. And it is beautiful and strange and utterly unlike anything in our everyday experience. Consider the holographic principle, one of the most profound ideas in modern physics. It says that all the information contained in a volume of space can be encoded on the surface bounding that volume. This seems absurd at first. How can a three-dimensional region of space have its information stored on a two-dimensional surface? But the principle arises naturally from the study of black holes. In the 1970s, Stephen Hawking and Jacob Bekenstein showed that black holes have entropy, a measure of the amount of information they contain. Remarkably, the entropy of a black hole is proportional not to its volume, but to the area of its event horizon. A bigger black hole has more entropy, but the increase is proportional to the increase in surface area, not volume. This suggests that the fundamental degrees of freedom, the basic units of information, lie on the horizon, not in the interior. This idea was generalized by Gerard Hooft and Leonard Susskind into the holographic principle, which applies to any region of space, not just black holes. It says that the maximum amount of information in a region is determined by the area of its boundary, measured in Planck units. The interior, in some sense, is a projection, a hologram, of the information on the boundary. Our three-dimensional universe might be a holographic projection from a two-dimensional surface at the edge of space, or perhaps at the edge of time. This principle has been made mathematically precise in certain contexts, particularly in the AD-CFT correspondence, a conjecture proposed by Juan Maldacena in 1997. It states that a theory of gravity in a particular type of curved space-time, called anti-de Sitter space, is exactly equivalent to a quantum field theory without gravity living on the boundary of that space. Gravity in the interior is dual to quantum field theory on the boundary. This is a powerful tool for studying quantum gravity because it translates difficult problems in gravity into easier problems in quantum field theory. It has led to many insights and is one of the most active areas of research in theoretical physics today. The holographic principle suggests that space-time, and even the dimension of space, might be emergent. The fundamental description might involve fewer dimensions than we perceive. What we think of as motion through three-dimensional space might actually be a holographic projection from a lower dimensional theory. This is a stunning idea, and while it is not yet proven for our actual universe, it is strongly suggested by the mathematics of black holes and quantum gravity. All of this points toward a deep truth. The concepts we use to describe reality, space, time, position, distance are useful but not fundamental. They work beautifully at everyday scales and even at extreme scales of galaxies and atoms. But they are approximations, emerging properties of a deeper quantum structure. At the Planck scale, the approximation breaks down, and we must let go of our familiar concepts and embrace something new. This is challenging because our brains evolved to navigate a world of medium-sized objects moving at medium speeds. We have strong intuitions about space and time, about here and there, about before and after. But intuition is not a reliable guide to the deep structure of reality. The history of physics is full of examples where intuition had to be abandoned in favour of mathematical rigour and experimental evidence. Newton's mechanics, which seems so intuitively right, had to be replaced by Einstein's relativity. The deterministic clockwork universe of classical physics had to be replaced by the probabilistic quantum world. And now, space-time itself, the very stage upon which physics plays out, must be replaced by something more fundamental. This is not a loss, it is a gain. Every time we have let go of an old concept and embraced a new one, we have gained a deeper understanding of the universe. We have seen further, understood more, connected, seemingly unrelated phenomena. The unification of electricity and magnetism, the equivalence of mass and energy, the entanglement of quantum particles, these were all surprising, counterintuitive discoveries that expanded our understanding in profound ways. The emergent nature of space-time will be another such expansion, perhaps the deepest yet. And it will change not just physics, but our entire worldview. If space is not fundamental, if distance is an illusion arising from quantum entanglement, then what does that mean for our understanding of existence? What does it mean for our sense of self, for our relationships with others, for our place in the cosmos? These are philosophical questions, and physics alone cannot answer them, but physics can inform them, can provide a framework within which to think about them. We are not separate from the universe, observing it from outside. We are part of it, made of the same quantum fields, subject to the same laws. Our consciousness, our thoughts, our feelings, all arise from the interactions of particles and fields. All are manifestations of the underlying quantum structure. We are localized patterns of information, temporary configurations of matter and energy, experiencing the universe from a particular perspective. And yet, we are also part of the whole, connected through the quantum entanglement that weaves space itself, participants in the grand unfolding of cosmic history. This is the picture that emerges from modern physics, from quantum mechanics and relativity and the quest for quantum gravity. It is a picture of profound interconnection, of unity underlying apparent separation, of simplicity giving rise to complexity. And it is a picture that inspires wonder, that reminds us of the deep mystery at the heart of existence, the mystery of why there is something rather than nothing, of why the universe has laws, of why we are here to ask these questions. As we probe deeper into the structure of reality, as we approach the Planck scale and contemplate the quantum foam, we are not just learning about physics. We are learning about ourselves, about our capacity for understanding, about the power of human reason and imagination. We are discovering that the universe is knowable, at least in part, that its secrets can be unlocked through careful thought and observation and mathematics. This is a remarkable gift, a privilege granted to conscious beings in a lawful cosmos. Conclusion. Standing at the edge of knowledge. We have journeyed together through one of the deepest and most fascinating frontiers in all of science. We have explored the Planck length, that unimaginably small scale where the laws of physics as we know them begin to dissolve into something new, something quantum, something we are only beginning to understand. We have seen how the simple act of observation, pushed to its limit, becomes impossible due to the interplay of quantum uncertainty and gravitational collapse. We have discovered that space and time, those seemingly solid foundations of reality, are not fundamental but emergent, arising from deeper quantum processes we have not yet fully grasped. Throughout this exploration, we have been guided by two great theories, quantum mechanics and general relativity. Each is spectacularly successful in its own domain. Quantum mechanics describes the behavior of particles and fields at the smallest scales, explaining atoms, molecules, chemistry, electronics, and much of the modern technological world. General relativity describes gravity and space-time, explaining the orbits of planets, the bending of light around massive objects, the expansion of the universe, and the existence of black holes. Both theories have been tested countless times and have never failed. And yet, they are incompatible. They speak different languages, rest on different principles, make different assumptions about the nature of reality. Quantum mechanics is probabilistic, dealing with wave functions and superpositions and uncertainties. General relativity is deterministic, dealing with smooth curves in space-time, with geodesics and curvature. Quantum mechanics treats time as a fixed parameter, ticking forward at a steady rate. General relativity treats time as part of space-time, flexible and dynamic, flowing faster or slower depending on gravity. These differences are not just technical details. They are fundamental incompatibilities that must be resolved if we are to have a complete understanding of nature. The Planck scale is where these two great theories collide, where neither can be ignored, where both are essential. It is the frontier of knowledge, the place where we must find a new theory, a theory of quantum gravity that unifies the quantum and the gravitational into a single, coherent framework. Many brilliant minds have devoted their lives to this quest. Many approaches have been tried, from string theory to loop quantum gravity to the holographic principle and beyond. We do not yet know which, if any, is correct. We do not yet have the complete theory. But we are making progress, slowly and steadily, guided by mathematics and logic and the occasional flash of insight. And as we make this progress, we are learning something profound. We are learning that reality is far stranger, far more subtle than we ever imagined. The solid, tangible world we experience in our daily lives, the world of objects occupying positions in space and moving through time, is a kind of approximation, a macroscopic average over countless quantum fluctuations. It is like the smooth surface of a lake, which appears continuous and calm from a distance, but is actually made of discrete molecules, jostling and bouncing chaotically up close. Space and time are like that smooth surface. They appear fundamental, but they are not. They emerge from something deeper. What is that deeper something? We do not fully know yet, but we have clues. It might be quantum entanglement, the sharing of information between quantum systems. It might be a network of loops and nodes, a discrete quantum geometry. It might be vibrating strings in 10 or 11 dimensions. It might be something we have not yet imagined. But whatever it is, it does not involve space and time as fundamental entities. Those emerge only in the appropriate limit, when we zoom out, when we average over many quantum degrees of freedom, when we look at the universe from a macroscopic perspective. This is a humbling realization, but it is also an empowering one. It tells us that the human mind, this extraordinary organ that evolved to help us find food and avoid predators on the African savanna, is capable of reaching beyond its evolutionary origins and grasping truths about the fundamental nature of reality. With nothing but thought and mathematics and careful observation, we can peer into realms utterly removed from everyday experience. We can contemplate the Big Bang, the expansion of the universe, the quantum foam, the fabric of space-time itself. This is one of the greatest achievements of our species, a testament to the power of curiosity and reason. And it reminds us that science is not finished. We do not have all the answers. There are deep mysteries remaining, questions that may take decades or centuries to resolve. What is the correct theory of quantum gravity? How did the universe begin? Is there a multiverse, other universes beyond our own? What is dark matter? That invisible substance that outweighs visible matter by 5-to-1? What is dark energy? The mysterious force causing the expansion of the universe to accelerate. These questions are open, awaiting answers, and that is exciting. It means there is still work to do, still discoveries to be made, still new realms to explore. But even as we acknowledge how much we do not know, we can also celebrate how much we do know. We understand the structure of atoms, the forces that bind them, the particles that compose them. We understand the life cycle of stars, from their birth in clouds of gas to their death as white dwarfs, neutron stars, or black holes. We understand the evolution of the universe, from the Big Bang through the formation of galaxies and planets to the present day. We understand the principles of quantum mechanics and relativity, even if we have not yet unified them. We have built telescopes that can see to the edge of the observable universe, and microscopes that can see individual atoms. We have sent spacecraft to other planets, landed rovers on Mars, flown probes past the outer planets and into interstellar space. We have detected gravitational waves from colliding black holes, photographed the shadow of a supermassive black hole, mapped the cosmic microwave background radiation. These are astonishing achievements, monuments to human ingenuity and perseverance. And now, as we stand at the Planck scale, at the boundary of knowledge, we find ourselves in a familiar position. Throughout history, whenever we have reached what seemed like a final limit, whenever we thought we had seen everything there was to see, we have discovered new layers, new depths, new frontiers. Atoms were once thought to be indivisible, but they contain nuclei and electrons. Nuclei were once thought to be fundamental, but they contain protons and neutrons. Protons and neutrons were once thought to be elementary, but they contain quarks and gluons. Each time we pushed deeper, we found more structure, more complexity, more beauty. Now we have reached the Planck scale, and we are finding that space and time themselves are not fundamental. What lies beyond this limit, we do not yet know. But if history is any guide, it will be something remarkable, something that challenges our intuitions and expands our understanding in ways we cannot yet imagine. And the journey toward that understanding is part of what makes us human. The desire to know, to explore, to push against the boundaries of the unknown is one of our deepest and most noble impulses. So what truly happens at the Planck length? The honest answer is that we do not yet fully know. We have ideas, hypotheses, mathematical frameworks, but we do not have a final, tested, confirmed theory. We know that space-time becomes quantum, that distances and durations lose their classical meaning, that new physics must take over. We know that the smooth geometry of Einstein's relativity gives way to quantum foam, to fluctuations and uncertainties. We know that black holes form if we try to probe too deeply, that measurement itself becomes impossible beyond a certain threshold. We know that space and time are likely emergent, arising from deeper quantum structures, but the complete picture, the full story, remains to be written. And that is as it should be. Science is not a collection of final truths, but an ongoing process of exploration and discovery. It is a conversation between humanity and the universe, a conversation conducted through experiments and observations and calculations. The Planck length is the current edge of that conversation, the place where our questions become most acute, where our ignorance is most profound, where the potential for discovery is greatest. As we continue this conversation, as we build better instruments and develop better theories and perform more precise experiments, we will learn more. Future gravitational wave detectors might reveal signatures of quantum gravity, tiny deviations from Einstein's predictions caused by the granular structure of spacetime. Future particle colliders, if we ever build them large enough, might probe closer to the Planck scale and discover new particles, new forces, new phenomena. Future mathematical breakthroughs might reveal connections between string theory and loop quantum gravity, might show how different approaches are different aspects of the same underlying truth. The journey continues. And in the meantime, we can appreciate where we are. We can stand in awe of a universe that is so richly structured, so mathematically elegant, so full of surprises. We can feel gratitude for the opportunity to be conscious beings in this cosmos, able to contemplate its mysteries and seek its truths. We can honor the countless scientists who have come before us, who built the foundations of our current understanding, who struggled with difficult problems and sometimes failed, but whose work paved the way for future discoveries. And we can commit ourselves to carrying that torch forward, to asking questions, to seeking answers, to pushing against the darkness of ignorance with the light of knowledge. If this quiet journey into the heart of physics has brought you even a moment of peace, even a spark of wonder, then I am deeply grateful you came along. These questions about the nature of space and time, about the limits of measurement, about the quantum structure of reality, are not just abstract puzzles for physicists. They are questions about the universe we all inhabit, about the fabric of existence itself. They touch something deep in the human spirit, that sense of wonder at the natural world, that desire to understand our place in the cosmos. A gentle like, a soft tap on subscribe, these are more than just gestures in the digital realm. They are quiet signs that these stories matter, that the pursuit of knowledge has value, that there are still people who pause in their busy lives to contemplate the deep mysteries of existence. Every small act of support helps keep this corner of the universe glowing, helps ensure that these conversations can continue, and for that I am profoundly grateful. If you would like, please share where in the world you are listening from tonight. Are you in a quiet room late at night, letting these ideas wash over you as you drift towards sleep? Are you on a morning commute, starting your day with thoughts of quantum foam and emergent spacetime? Are you a student studying physics, finding inspiration for your own journey into the unknown? Wherever you are, whatever your circumstances, know that your presence here matters. You are part of a community of curious minds scattered across this planet, all looking up at the same stars, all wondering about the same deep questions. Your words, your presence, are like small lights across the dark and endless sky, reminders that we are not alone in our wonder. Wherever you may be, take a moment to notice your breath. Notice the space around you, the quiet hum of existence, the subtle awareness that you are here, conscious, listening, present. This moment, this simple act of paying attention, is something extraordinary. In a universe filled with oceans of silence and vast stretches of empty space, your awareness is a tiny flame of meaning. It flickers, it questions, it reaches out, and in doing so, it becomes part of something larger, something deeply human. Perhaps you are curled beneath a blanket, letting the soft glow of your screen illuminate a small pocket of the night. Perhaps the world outside your window is dark and still, and you can almost imagine the Milky Way drifting silently overhead. Maybe you are lying in bed, your mind finally slowing after a long day, letting these ideas guide you gently towards sleep. If so, I hope these words feel like a companion, steady, calm, and unhurried, walking with you through the mysteries of the universe. Or maybe you are listening during daylight hours, surrounded by the familiar rhythm of life. You could be at a desk with headphones on, searching for a moment of stillness amid responsibilities. Maybe you are traveling somewhere, watching landscapes or city streets pass by, letting these ideas transform an ordinary moment into something just a little more wondrous. And if you are a student or a lifelong learner, maybe these concepts spark that quiet excitement inside you, that feeling that the universe still has secrets waiting for you to uncover. No matter where you are, know this: your curiosity is powerful. It ties you to every scientist who ever looked through a telescope, to every thinker who ever wondered what lies beneath the surface of reality. It connects you to countless others who have asked the same questions, felt the same awe, dreamed the same dreams. Even if you are physically alone right now, you are not alone in your wonder. So let this moment be an invitation to slow down, to breathe, to imagine yourself drifting outward beyond the boundaries of daily life, past the world you know, into the deep and mysterious architecture of space-time itself. Let your thoughts float like stardust, weightless and unhurried, as together we step into the smallest scales the universe has to offer. Thank you for exploring with me. Thank you for your patience with the difficult concepts, your willingness to venture into realms far removed from everyday experience, your openness to ideas that challenge intuition and common sense. The Planck length is not an easy topic. It sits at the intersection of our two most difficult theories, quantum mechanics and general relativity. It demands that we think in unfamiliar ways, that we let go of cherished concepts like the absolute nature of space and time. But you have stayed with me through this journey, and I hope it has been rewarding. Until next time, rest well. Let your mind drift gently through the cosmos, through the quantum foam and the curved space-time, through the networks of entanglement that might underlie reality itself. Let yourself feel the wonder of existence, the astonishing fact that the universe is here, that we are here, that we can ask these questions and glimpse, even if only dimly, the answers. May your dreams tonight be filled with stars and strings and loops of quantum geometry. May you find peace in the knowledge that the universe is knowable, that its mysteries invite us to explore them, that the journey of understanding is itself a profound gift. And may you remember, always, that you are made of stardust, that the atoms in your body were forged in the hearts of ancient stars, that you are intimately connected to the cosmos at every level, from the vast expanses of space to the quantum foam at the Planck scale. You are not separate from the universe, you are part of it, a way for the cosmos to know itself, as Carl Sagan so beautifully said. And in that knowledge there is comfort and wonder and a deep sense of belonging. Rest well, dear listener, the stars will be waiting when you wake. The mysteries of the Planck length will still be there, inviting future explorers to probe deeper, to ask better questions, to find new answers. And you, with your curiosity and your willingness to wonder, are part of that great adventure. Thank you for being here. Thank you for caring about these questions. Thank you for sharing this journey through the quantum frontier. Until we meet again among the stars and the equations, sleep gently, dream deeply, and may the universe continue to reveal its secrets, one Planck length at a time.